and welcome to this video on acid-base strength. My name is Kim, and in this video we'll be describing how to calculate Kb for a weak base. We discussed in other videos how to draw the dissociation reaction for a weak base, as well as the kinds of equations necessary for calculating Ka for weak acids. And in this video we're going to do something very similar and calculate some information about weak bases, namely the base dissociation constant Kb. All K constants are equal to the concentration of the products over the concentration of the reactants. So for the generic weak base B, the Kb will equal to the concentration of the conjugate acid BH+, multiplied by the concentration of the hydroxide ion, divided by the concentration of the conjugate base B. Notice that water does not appear in the K expression. Remember that pure liquids and solids do not factor into K equations. Like the video describing Ka for weak acids, the same two methods will exist for calculating Kb. If we're given the pOH and the concentration of the base, we can use an ice table and calculate the concentration of hydroxide ions from the pOH equation. That way we can identify the variables in the Kb expression and solve for Kb. If you're a bit wobbly with ice tables, I would recommend pausing here and reviewing the steps for constructing and calculating the values in the videos that review ice tables, since those are going to be necessary to calculate Kb. Alternatively, given the percent ionization and the initial concentration of base, we can set up an ice table, then calculate the concentration of the products of dissociation using the percent ionization, and then plug those values into the Kb expression and solve. Let's take a look at an example of both methods. This applied question asks us to calculate the Kb given the concentration of base and the percent ionized at equilibrium, which means we need to use the second method described earlier. The first step is to create the dissociation reaction of methylamine and water. So methylamine will accept a proton from water to form methylammonium and the hydroxide ion. The Kb expression will be the concentration of the products over the concentration of the reactant, excluding water. Next, set up the ice table. The initial methylamine is 0.75 and will be 0 for hydroxide and for methylammonium. The change will be minus X for methylamine plus X for both hydroxide and for methylammonium, since for every molecule of methylamine you protonate, you form one molecule of hydroxide and one molecule of methylammonium. The equilibrium concentration will be 0.75 minus X, and again plus X for hydroxide and for methylammonium. Third, let's calculate how much dissociates at equilibrium. Take the percentage and convert it to a decimal, so 0.0085 multiplied by the initial concentration of 0.75 to get 6.38 times 10 to the minus 3. That is a concentration of the products of the dissociation, which is X. We can now use this to fill in our table. So 6.38 times 10 to the minus 3 for hydroxide. Same thing for the methylammonium. And the equilibrium concentration of methylamine will be 0.75 minus 6.38 times 10 to the minus 3. Our last step is to fill in the Kb expression from earlier using the values in the table. So the same Kb expression from earlier with the filled in values from the table gives us a Kb value of 5.47 times 10 to the minus 5. This is the relative proportion of the products to the reactants, and since the value is a fraction of 1, we know that this is indeed a weak base and methylamine will stay mostly deprotonated in solution. This next question asks for the Kb of the same methylamine given a concentration and a pOH value. We need to use the first method described earlier. First step is to draw out that dissociation reaction and the Kb expression, which we already did. Next is to set up the ice table and to fill it in. Initial concentration for the methylamine is 0.3 molar. It's going to be 0 for the hydroxide and for the methylammonium. The change will be minus X for methylamine and plus X for hydroxide and for methylammonium. And the equilibrium concentration will be 0.3 minus X, and again plus X for the hydroxide and for the methylammonium. Next, we need to use the pOH information to calculate the concentration of hydroxide. Since pOH is equal to the negative log of the concentration of hydroxide, rearrange to solve for hydroxide, which is equal to 10 to the negative pOH. 10 to the negative 2.35 is equal to 4.46 times 10 to the minus 3. And since the hydroxide concentration will equal the methyl ammonium, we can start filling in our table. So 4.46 times 10 to the minus 3 for hydroxide. Same thing for methyl ammonium. And the equilibrium concentration for methylamine will be 0.3 minus 4.46 times 10 to the minus 3. Finally, solve for Kb using the expression described earlier and the new calculated values from the table. Filling in the expression, we get this equation, and plugging those values into a calculator gives us Kb for the methylamine of 6.77 times 10 to the minus 5. Just like earlier, Kb here shows us that since the value is much less than 1, methylamine prefers to stay as methylamine in water. Great job working through these calculation steps. While these two methods might initially seem different, we can see that other than the information used to calculate the hydroxide ion, the steps are mostly the same. Make sure you follow this up with some practice.